Hello students, welcome to EPG Pathshala. I am Ashok Goyal from the Department of Physics and Astrophysics, University of Delhi. Today we are going to discuss about infinite and continuous groups from the paper Mathematical Physics. You are going to learn in this module about the groups which are based on the theory of angular momentum in quantum mechanics, namely the group O3 or SU2 or SU3, which are the groups of rotation in 3 dimensions. For example, the group SU3 is used to describe the hadron spectrum in quark model. These and other groups used in particle physics and general theory of relativity have infinite number of continuously varying groups. That is, the groups like SU2, SU3, SU5, they have applications in particle physics and they have infinite number of continuous and varying elements. You will further learn in this module about the generators and representations of continuous groups. These groups and others which are used in particle physics and in general theory of relativity have infinite number of continuously varying elements. That is what is meant by continuous group. The elements vary continuously. So in this module, you will learn about the generators of these continuous groups. So what is an infinite group? An infinite group contains an infinite number of elements. If the number of elements is denumerably infinite, then the group is called discrete, like the group of all real numbers. Whereas if the number of elements is non-denumerably infinite, then it is called a continuous group. For a continuous group, it is convenient to label the group elements by one or more real parameters, which are called group parameters. That is, the group G is a function of the elements, group elements A, and the element A in turn is a function of certain group parameters alpha 1, alpha 2, etc. It can be, for example, just a function of one parameter. A continuous group is one in which the parameters take continuous values. The number of independent parameters define the dimension of the group, and that is called the order of the group. So if you have the elements of the group depending on two independent parameters, then the order of the group is 2 and its dimension is 2. It is not the same thing as the dimension of the matrices of the representation. Having defined the continuous groups, we will now give some examples for a better understanding. Example number 1. A set of all real numbers R is a continuous group of order 1 under addition, because any element of the group which is a real number can be characterized by just one parameter x, which takes values from minus infinity to infinity. So a real number set is a continuous group of order 1 under addition. If from this set we define a set R star without the 0, then this set is also a continuous group of order 1 under multiplication. Notice that it is a one parameter group. Therefore, is a group of order 1. As a second example, consider a set of all rotations about an axis. Now this forms a continuous group again of order 1, whose parameter is chosen to be the angle of rotation theta, which varies from the interval 0 to 2 pi. The group element R theta is a function of the group parameter theta. This group is denoted by a set of real, orthogonal, 2 by 2 non-singular matrices with determinant 1. Such matrices are called SO2. The group elements are represented by the matrices R theta given by a 2 by 2 matrix with entries cosine theta, sine theta, minus sine theta and cos theta, which, if you remember, represents a rotation by an angle theta in the xy plane about the z-axis, which takes a vector in two-dimensional space xy to x prime y prime, and the group elements and the matrices satisfy the group multiplication, that is r theta 1 r theta 2 is given by r of theta 1 plus theta 2, that is a rotation by an angle theta 2 followed by a rotation by an angle theta 1 is equal to a rotation by an angle theta 1 plus theta 2. Yet another example is a linear homogeneous transformation of n variables xi. The rotation in which we had considered earlier is a transformation of two variables. Now, if we have a linear homogeneous transformation of n variables xi, I goes from 1 to n, then this transformation can be represented by a matrix A such that the matrix A operating on these variables xi, which we can write in the form of a vector, transforms to the vector xi prime. That is, xi prime is equal to aij xj sum over all j's 1 to n, and the transformations are such that the modulus aij is not equal to 0. This transformation constitutes a continuous n-square parameter group known as the linear n-dimensional group denoted by G-Ln. This n-square parameter group G-Ln is isomorphic to all n by n non-singular matrices under multiplication. Okay, let us define Lie groups. The Lie groups are continuous groups, but they have the additional property, and that is the elements of this group are functions of the parameters that are smooth, differentiable, and analytical. So, Lie groups are most important groups in physics. Where do they occur? In physics. They occur in quantum mechanics, in particle physics, in condensed matter physics, and in string theories, etc. So, let G be a continuous group whose elements A are functions of continuous group parameters. That is, G is a group whose elements are functions of some parameters alpha 1, alpha 2, and the elements are continuous functions of these parameters. And these parameters are defined, let us say, in R, which is a set of all real numbers. Let M be a continuous n-dimensional space in R, which is called the parameter space. A point in this parameter space is specified by the coordinates, that is, by n tuple of numbers, one each for the parameters. It's a parameter space. So, every point in this represents the value of the parameter, which are the parameters for the group. That is, a point, for example, represents the value of the parameters alpha 1, alpha 2, alpha n, etc. We assume that the origin of this coordinated space in the parameter space represents the identity element. That is, the identity element A is defined for all the parameter equal to 0. So, E is equal to A evaluated at 0, 0, 0. If A and B are 2 points in the parameter space of G, that is, the 2 point A and B belong to the parameter space M, then corresponding group elements are A, a function of parameter point A, and B of B, and they should satisfy the same group multiplication laws as do the elements A. The two elements of a Lie group, A and B, satisfy the group multiplication law that the element A, which is a function of a parameter A, multiplied by the element B of B is equal to an element which also belongs to the group C, evaluated the parameter C, for all parameters A, B, and C which lie in the parameter space. That is, A, B, C are points in the parameter space, and the elements of the continuous group, which are functions of these parameters, satisfy the group multiplication law. Since the group we have considered is a continuous group, the parameter C must be a continuous function of A and B. That is, C, the parameter C as a function of AB must be a continuous function that maps 2 points AB in the group G to a third point C. And if this function AB is an analytic function in both the variables, then the group G is a Lie group. Thus, for the Lie group, we have AB related by a continuous function to the parameter C, in which wherein the points AB in the group map to the point C. And this relationship is analytic. In other words, a Lie group is a continuous group with the added property that the elements of the group are not only continuous, but the group mapping law is analytical, which means the law which maps the group has an analytical relationship and therefore can be differentiated or integrated. The number of independent parameters of such a group is called its dimension. For a continuous group like a Lie group, it is possible to find a set of generators which allows us to generate the whole group. The knowledge of generators is as good as knowing the whole group. It is convenient to choose the continuous parameters of a Lie group in the parameter space M in such a way that the identity element E is the origin of the parameter space. So what are we trying to say? We are trying to say that for a Lie group, it is possible to find the generators. The number of generators for a Lie group is generally fixed and small. And once these generators are known, any group element can be generated from that. So how is it done? We define a parameter space M. Any point in that parameter space gives value for the parameters, and we define the identity element E as the origin of this parameter space, which means that the identity E is defined as the element evaluated at the origin of the parameter space M. So E is equal to A evaluated when all the coordinates in the parameter space are put equal to 0, A, 0, 0, 0 for an n-dimensional Lie group, where n is the number of parameters. Let us, for simplicity, consider an element of the group which is near the identity. And let us, for simplicity, consider the case where all the elements are 0 except the rth element. And the rth element is infinitesimal in magnitude. That is, we have the elements alpha r and alpha 1, alpha 2, alpha r minus 1, alpha r plus 1 and alpha n are all 0. We have n parameters, alpha 1, alpha 2, alpha n. All the parameters are 0 except the parameter alpha r, which is infinitesimally small, and we write that as epsilon r. Then the group element then is given by A 0, 0 for all the parameters except the value of the rth parameter, which is epsilon r. And since this relationship is analytical, we can write A 0, 0 epsilon r 0, 0 as A evaluated for all values of parameters 0 plus I times epsilon r, some function which we call t, some operator which we call t of r at 0, 0, 0. For example, it's something like the Taylor expansion, that if you have a function of, for example, of one variable, then the value of the function at the point x plus h, where h is infinitesimally close to x, is given by the value of the function of x plus h times the derivative of the function with respect to x evaluated at the point x, where all the other terms 0. So it's something like the first term in the Taylor expansion. So we have this element evaluated at infinitesimal parameter epsilon r equal to the element where all the parameters are 0 plus this infinitesimal amount multiplied by an operator tr to first order epsilon r. Due to the analytical property of the Lie group, the operator tr is called the generator of the Lie group, and it can be written from this expressed as tr is equal to 1 upon epsilon r of the difference of the group elements with the value, infinitesimal value of the parameter epsilon r minus the group element for all parameter value 0 in the limit that epsilon r goes to 0. So this is defined as the generator. So having defined the generator, if you want to generate an element of the group for a finite value, our aim is to generate elements of the group for a finite value of the elements, not for an infinitesimal value of the element. So we want to generate an element of the group for a finite value that is a finite distance away from the identity. So suppose we want to generate an element for the parameter AR, which is n times, which can be generated by multiplying infinitesimal value epsilon r by this n, that AR is equal to n epsilon r, where n is a positive integer, and if we take n going to infinity, for epsilon r going to 0, we can generate the element for a finite value AR. Thus, the element for a finite value AR of the Lie group for all other parameters 0, namely A00 AR0, can be obtained from the infinitesimal element multiplied n times. So this is equal to A00 epsilon r raised to the power n. So A0 can be written as A00 minus I epsilon, the generated tr raised to the power n, which is the identity, plus I AR by n multiplied by generator raised to the power n, and the limit n goes to infinity. Therefore, the element for a finite value of the parameter AR can be written as exponential of IAR TR, where TR is the generator defined earlier, because the limit of 1 plus x by n to the power n as n goes to infinity is exponential x. Thus, for a general generator of the group, we have, because of the analytic nature of the elements on all parameters, the group element evaluated at finite values of the parameters 1, 2, 3, n etc. the n parameters. If we want to generate an element of the group for parameter values a1, a2, an, then this can be written as exponential of I, ai, ti, where I is summed over 1 to n, where ti are the generators. Thus, a Lie group with n independent continuous parameter has n generators. That is, the generators of the group can give us all the elements, and a Lie group with n independent parameters has n generators. So there are certain corollaries which follow. The infinitesimal element of a Lie group constitute an Abelian group. This is important. The infinitesimal element of the Lie group is Abelian. Consider, for example, the rth and the sth elements AR and AS. Then the element AR is given by putting the value of all parameters except the rth parameter non-zero and infinitesimal. That is, AR is equal to AR 0, 0 for all parameters except the rth parameter, for which we put the value epsilon r, which is infinitesimal, so it can be expanded, like for example in a Taylor series, keeping only the first term as the identity element E plus I epsilon r into something TR, which we call as a generator of the group. And likewise, AS is equal to E plus I epsilon S TS. And you can see now that if you take the product of the two elements AR and AS, then AR and AS is approximately given by identity plus I times epsilon TR plus epsilon S TS, where the terms of order epsilon square have been neglected, and you can see from here that epsilon R AR AS is equal to AS and AR. That is, they are abelian, they commute. Infinitesimal elements commute among themselves. That is, AR AS is equal to AS AR for infinitesimal elements of the group. Now we talk about the representations of the continuous group. Let G be a continuous group, and let X and X prime be 2 points in the parameter space, because we have already explained that the elements of the group can be specified by the points in the parameter space. So let X and X prime be 2 points in the parameter space M. The group elements are then characterized by points X, X prime, etc. in M. The representation written as gamma X is then characterized by the same parameters as used for characterizing the group elements. In a Lie group, as parameters change continuously from X to X prime in the parameter space, the corresponding representation matrices gamma X also go continuously to gamma X prime. And moreover, the matrix elements, being analytical functions of the parameters, now allow us to state a theorem which will do so without giving the proof. The theorem is that any representation of a Lie group has an equivalent representation whose matrices are unitary. You already know that we can always choose a unitary representation of a finite group. So just as for finite groups, for the Lie groups also, any representation has an equivalent representation whose matrices are unitary. Further, any unitary representation is completely reducible. That is, it can be brought to the block diagonal form, as in the case of finite groups. Any irreducible representation, further, is a finite dimensional representation. So all representations which are reducible are finite dimensional representations, and any representation which is not irreducible can be brought completely in a block diagonal form and can be reduced to a sum of irreducible representations. Having defined the representation of the continuous group, we will now consider a few examples to illustrate what we mean. Consider a set of rotations about a fixed axis normal to the plane of a circle. Let the rotation be about an axis which is passing through the center and is normal to the plane. This group of rotation is a one-parameter group, continuous group, and this is indeed a one-parameter continuous Lie group. And this group is designated as SO2, that is rotations in two-dimensional space. The parameter space in this case can be visualized as points on the unit circle labeled by the angle theta, where theta lies from between 0 and 2 pi. The group element r theta, which is a rotation by an angle theta about the g-axis, this is characterized by one parameter theta. So, an element corresponding to rotation theta 1 is characterized by r theta 1, and these group elements obey the multiplication law, which means the product of two elements r theta 1 and r theta 2 is equal to the element theta 1 plus theta 2, which means that a rotation by an angle theta 1 followed by a rotation by an angle theta 2 is equal to a rotation followed by an angle theta 1 plus theta 2. Clearly, this is an abelian group. Because whether we first rotate about theta 1 and then theta 2, or we first rotate by an angle theta 2 and then by theta 1, the result is always the same. That is a rotation by angle theta 1 plus theta 2, which means that r theta 1 into r theta 2 is equal to r theta 2 into r theta 1 is equal to r theta 1 plus theta 2. And since it's an abelian group, and we have seen in the earlier modules that all its representations are one-dimensional. All the representations of the group SO2 are one-dimensional, and they are of the form that gamma theta is equal to exponential plus minus im theta, where m is an integer. For every integer value of m, we have an irreducible representations of the group SO2. A typical element r theta of the group can be written as r theta in the form of a 2 by 2 rotation matrix with matrix element cosine theta, sine theta, minus sine theta, cos theta. You are all familiar with this rotation matrix. What does it do? It operates on a vector xy in two-dimensional space, and it rotates this vector by an angle theta about the z-axis. That is, x prime y prime vector is given by cosine theta, sine theta, minus sine theta, cos theta operating on the vector xy. The matrix R theta is a 2 by 2 orthogonal matrix with determinant plus 1. So instead of rotation, suppose we consider a set of all 2 by 2 orthogonal matrices with the determinant 1, then obviously the set of 2 by 2 orthogonal matrices with the determinant 1 are isomorphic to the rotation group SO2. And clearly the matrices R theta provides a two-dimensional representation of the group SO2, whose all irreducible representations are one-dimensional. So we have seen that since the group SO2 is an abelian Lie group, all its irreducible representations are of one dimension. The representation R theta in the form of a 2 by 2 matrix is a two-dimensional representation, which obviously is a reducible representation. Now, interesting and important thing is to obtain the generators of the group. From the definition of the generator, T, this is a one parameter group, so it has only one generator. Let's call that generator T. Then from the definition of the generator given earlier, T is equal to the limit theta goes to 0 of 1 upon I theta of rotation of the element cosine given by the rotation matrix R theta, cosine theta, sine theta, minus sine theta. This divided by the identity, which is 1, 0, 0, 1. And if you take the limit of this, then becomes a 2 by 2 matrix, obviously, with the entries 0, minus 1 in the first row and I 0 in the second row, which you remember from your quantum mechanics class is the familiar Pauli matrix sigma 2 or sigma y. Now let us consider a group of all n by n matrices. The all n by n matrices are represented as M. A natural object for the matrix M is to operate on a column of a vector, which is a vector n-dimensional space because M is a n by n matrix. So the matrix M operating on this column vector x1, x2, xn takes it to another column vector x1 prime, x2 prime, xn prime given by the vector xi prime is equal to the matrix M ij xj, or in terms of explicit matrices is written as shown in the slide. So what does it do? It linearly transforms an n-dimensional target space with coordinates x1, x2, xn to a space with coordinates x1 prime, x2 prime, xn prime. If the group is a general linear group over the field of real n-dimensional space, the group is called GLNR, and the only constraints on the matrix elements Aij is that the determinant of the matrix should be non-zero. So there are no algebraic constraints on the elements Aij, and the transformation is analytic, and the dimensionality of the group is n square, because they are n square elements matrix. If the determinant is constrained to be 1, then the matrix M belong to the group SL and R, and its dimensionality is then reduced from n square to n square minus 1 because of the constraint of the determinant to be equal to 1. If the group has more constraints, say in the earlier example there is one constraint that the determinant is 1. But if the group happens to have more constraints, for example, if it preserves the quadratic form, that is, sum of the squares of the components of the vector x is invariant, that is, this transformation leaves magnitude or the square of the vector unchanged, invariant, then is a set of n cross n real orthogonal matrices. An orthogonal matrix being defined as a matrix M such that M transpose multiplied by M is equal to identity, and in this case the group is denoted by On. So On is the group of n by n orthogonal matrices. It consists of matrices with determinant plus 1, then is called a proper rotation. If the matrix had determinant minus 1, then it represents a reflection of x goes to minus x. The subgroup containing proper rotations is a n into n minus 1 by 2 parameter Lie group, which is denoted by SON. For example, the groups SO2, SO3 and SO4 have the dimensionalities, that is the number of parameters, which in turn is equal to the number of generators, are equal to 1, 3 and 6 respectively, from the expression that the number of independent parameters is given by n into n minus 1 by 2. For n is equal to 4 example, it is 6, and the SO4 has 6 parameters. In physical applications, we often come across unitary group of n by n unitary matrices. Here, in contrast to the earlier case, the target is a space of real numbers, but it is a space in a complex plane. That is, the space is Z, a space of complex numbers. And the column vectors u1, u2, u1 are defined over a set of complex numbers. And for unitary matrix, the quadratic form ui dagger ui, which is equal to u dagger u, which is equal to ui star ui, is preserved. In this case, the dimensionality of the group is n square. The special unitary group SUN is a unitary unimodular group, and because of the unimodular nature, its number of parameters is reduced as dimensionality is n square minus 1. So SUN is a unitary unimodular group of n square minus 1 parameters and has as many generators. So we are now in a position to summarize what we have learned in this module. What we have learned first and foremost is that a continuous group whose elements are functions of group parameters which are smooth, differentiable and analytical, such a continuous group is called a Lie group. And number 2, the irreducible representation of a Lie group are all finite dimensional. 3. The group of orthogonal matrices with determinant plus 1 is denoted by SON. This is a Lie group. Is a Lie group of orthogonal matrices of determinant 1 of dimension n and is denoted by SON. The number of parameters of this group is equal to the number of generators, which is equal to n into n minus 1 by 2. The group of unitary matrices with determinant plus 1 is denoted by the group SUN. It is an n square minus 1 parameter Lie group and has as many generators as the parameters. Thank you.